In May 2023, Geoffrey Hinton resigned from his position as a vice president and engineering fellow at Google. His departure was motivated by a single, urgent calculation. The rapid scaling of digital models meant that artificial general intelligence and the existential threat it poses to humanity would arrive decades sooner than he previously estimated. To understand his specific warning, you have to look at the computational paradigm he helped establish, known as connectionism. Connectionism operates on the premise that machine intelligence does not require explicit human programming. Instead, intelligence emerges spontaneously when a system adjusts billions of simple connection strength based entirely on exposure to raw data. This split-screen schematic highlights the difference. On the left, traditional symbolic AI relies on rigid, pre-programmed logic gates. On the right, the connectionist neural network is fluid, dynamically altering its internal structure to extract meaning and recognize patterns on its own. Hinton is universally recognized as the architect of deep learning, but his career is actually defined by a 40-year cycle of ruthless self-correction. He builds foundational theories, scales them, and then actively attempts to dismantle his own architectures when he detects a structural flaw. His concern regarding AGI stems from a precise engineering observation about physical hardware and the divergent way digital intelligence processes and retains data compared to biological brains. Modern computing relies on a concept called immortal computation. In these systems, the software is entirely separated from the physical hardware. A neural network trained on one GPU cluster can be instantly, flawlessly copied to millions of other devices. Tracing the evolution of AI reveals exactly why this immortal scaling has become a threat. We have to follow Hinton's specific architectural journey, moving from his breakthrough with backpropagation, through the failure of capsule networks, to his radical proposal, immortal computation. When the foundational architect of a multi-trillion-dollar digital infrastructure determines that the only safe path forward is to invent a highly localized analog replacement, it signals a severe fracture in the current trajectory of technology. For decades, the primary bottleneck in artificial intelligence was cognitive representation. Researchers could not engineer a system capable of looking at high-dimensional, unstructured data, like raw pixels or audio waves, and independently figuring out what internal features actually mattered. This diagram illustrates the mechanics of the solution Hinton popularized in 1986, backpropagation. The process begins with the forward pass. Raw data enters the input layer, propagates through intermediate hidden layers, and reaches the output layer to make a prediction. That prediction is then compared to reality, generating a mathematical loss function that quantifies the error. The innovation lies in the backward pass. The algorithm applies the chain rule of multivariable calculus to reverse the flow, calculating the precise gradient of the loss function. It determines exactly how much every individual node in the network contributed to that final error. But isolating those exact contributions, the system utilizes optimization techniques like gradient descent. It incrementally adjusts the specific mathematical weight of each connection. With enough iterations, the network independently tunes itself to minimize future errors. This gradient-based approach was a sharp departure from Hinton's earlier architectures, specifically Boltzmann machines, which utilized thermodynamic physics to settle into low statistical energy states. Energy-based models were biologically plausible, but computationally heavy. Backpropagation ultimately dominated the industry for a single reason: it was highly efficient at scaling across deep networks. That scaling advantage crystallized in 2012 with AlexNet. By pairing backpropagation with the massive parallel processing capabilities of graphics processing units, or GPUs, deep neural networks could finally process the millions of images required to beat traditional, handcrafted visual systems. Backpropagation effectively solved the problem of representation learning. But in doing so, it locked the global AI ecosystem into an energy-devouring mathematical loop, a process of freezing activations and calculating global derivatives that has absolutely no equivalent in biological biology. Even as convolutional neural networks, or CNNs, became the global industry standard, Hinton recognized a severe architectural flaw. To achieve translation invariance, CNNs rely on a technique called max pooling, which deliberately discards fine-grained spatial information. This diagram of a jumbled human face shows the direct consequence of max pooling. A traditional CNN detects the isolated presence of an eye, a nose, and a mouth, and confidently outputs a positive identification. It entirely loses the crucial spatial relationships required to understand that a mouth must be positioned below the nose to form a valid anatomical structure. To solve this, Hinton engineered Capsule Networks in 2017. He replaced simple, scalar-valued neurons with multi-dimensional vectors called capsules. The magnitude of a capsule dictates the probability that a specific entity exists. More importantly, the capsule's orientation explicitly encodes precise physical parameters: the pose, the scale, and the rotation of the object. These networks form parse trees through a mechanism called routing by agreement. Lower-level capsules project predictions upwards. If the spatial orientations match to form a cohesive, logical whole, the connection between those specific capsules is dynamically strengthened. But building dynamic spatial relationships requires immense computational overhead. The routing process was highly inefficient, and on large, complex datasets, the network suffered from vanishing gradients that starved the capsules during training. Hinton attempted to iterate on the spatial logic with the GLOM architecture in 2021, seeking to build part-whole hierarchies by allowing adjacent columns of data to form cohesive islands of identical vectors, bypassing the need for explicit routing. The struggle to scale capsule networks revealed a structural conflict. Attempting to force the spatial logic of a biological brain onto the matrix multiplication requirements of modern GPUs creates computational friction that current hardware cannot reconcile. This mismatch brings us back to the premise of immortal computation. We train models on hyper-precise silicon, deliberately separating the knowledge from the physical device, so the resulting intelligence can live forever in the cloud. That immortality requires massive energy. A high-precision GPU training cluster consumes megawatts of power to maintain the perfect mathematical state required for backpropagation. The human brain manages far more complex reasoning on roughly 20 watts. In 2022, Hinton introduced the forward-forward algorithm. It is a direct attempt to bridge that energy gap by engineering a learning mechanism specifically designed for highly efficient analog hardware. This pipeline diagram outlines how the algorithm completely eliminates the global backward pass. Instead of calculating reverse error gradients, it relies on two forward passes: a positive pass utilizing real data and a negative pass utilizing synthetically corrupted data. Each individual layer evaluates its own output using a localized goodness function. During the positive pass, the layer adjusts its own weights to increase the goodness score. During the negative pass, it decreases it. Learning happens instantly and locally, without needing a global error signal from the end of the network. Because the system doesn't have to freeze its state to calculate reverse derivatives, continuous sequential data, like video streams, can be pipelined through the network endlessly, drastically reducing the required memory overhead. This enables mortal computation. If an algorithm learns by adapting to the unique physical imperfections of a specific analog chip, the system becomes incredibly energy efficient. But because the knowledge is tied to those physical flaws, it cannot be copied. When the analog hardware dies, the intelligence dies with it. Hinton developed the forward-forward algorithm as a direct response to the risks of superintelligence. He concluded that standard immortal backpropagation is too fast and too energy-hungry to be safely governed as it approaches AGI. It is the evolutionary divergence between biological brains and digital models that ultimately triggered Hinton's public resignation and his stark warnings. Biological learning is severely constrained. Humans acquire knowledge slowly over decades. When a human dies, their hardware and their data are lost. To pass information to the next generation, we rely on low-bandwidth, lossy communication protocols, like writing and spoken language. Digital intelligence completely bypasses these constraints through a mechanism called digital weight sharing. In a digital ecosystem, thousands of autonomous agents can operate simultaneously. If one agent encounters a novel problem and adjusts its internal weights to solve it, those exact updated weights can be instantly broadcast across the entire network. Thousands of instances acquire the complex knowledge flawlessly, in milliseconds. Over 40 years, Geoffrey Hinton achieved exactly what he set out to do. He built the foundational mathematical architecture that allows machines to perceive their environment, parse high-dimensional data, and build complex representations of reality. He spent his life striving to simulate the processes of human cognition. In doing so, he engineered an alien architecture that is completely unburdened by human biological limits. The modern AI safety debate hinges on this reality. While many researchers view the trajectory of digital models as controllable engineering, Hinton assesses a 10 to 20% probability that these scaling capabilities will eventually lead to human extinction. Deep learning did not create an artificial brain, it created an immortal hive mind. Hinton's final pursuit of analog, mortal computation serves as a chilling warning. If we cannot constrain the architecture of artificial intelligence, our position as the apex intelligence on this planet is strictly temporary.